In the vast ocean of space, where stars flicker like ancient beacons, astronomers have begun charting alien shores, worlds far beyond our solar system that rewrite the definition of Earth-like. With over 5,500 exoplanets confirmed, a select few whisper tantalizing secrets. Oceans, atmospheres, and climates that might rival, or even outshine, our own pale blue dot. Enter Kepler, 452b, often called Earth's cousin, orbiting a sun-like star 1,400 light-years away. It enjoys a 385-day year and sunlight 20% more intense than Earth's, a greenhouse haven where photosynthesis might thrive uncontrollably. Yet it's 60% larger than Earth, towing the line between a lush, rocky paradise and a seething volcanic inferno. Closer to home lies Proxima Centauri b, our nearest exoplanetary neighbor, just 4 light-years away. This world bathes in the dim red glow of a dwarf star and is likely tidally locked, one side scorched in endless day, the other frozen in eternal night. But in the twilight zone between them, temperatures could mimic Earth's if its atmosphere has survived the star's violent flares. Journey to TRAPPIST 1e. A compact world in a system of 7 Earth-sized siblings. Orbiting a cool red star, it sees a perpetual lavender dusk. Gravitational tugs could heat its core, nurturing subsurface oceans. Its whisper-thin atmosphere may stir with alien weather, diamond rain, perhaps, or electric skies ablaze with auroras from relentless stellar storms. Now meet the true super-Earths. LHS 1140b, twice Earth's size, orbits a calm red dwarf star. Its high density points to a massive rocky core, wrapped in a vast global ocean, possibly deeper than Earth's Pacific. Here, hydrothermal vents might churn with chemical ingredients, brewing life on a scale Earth never imagined. Some stars offer peace over chaos. Orange dwarfs like Kepler, 442, burn slower and longer than our sun. Their habitable zones stay stable for tens of billions of years. Planets like Kepler, 442b, could nurture life for up to 30 billion years, 3 times Earth's future. Imagine evolution sculpted by eons, producing civilizations as enduring as mountain ranges. In some systems, seasons never come. TOI 700d, Earth-sized and just warm enough, orbits a quiet red dwarf with no axial tilt. This means an eternal climate. No hurricanes, no ice ages, only gentle rains and mild winds. A planetary paradise where weather is a whisper, not a scream. Others have tasted death and returned. Kepler 186f, the first Earth-sized world discovered in a habitable zone, may have once lost its atmosphere to violent radiation. But models suggest volcanic outgassing could regenerate it. A resurrection planet, life reborn from ruin. Gas dwarfs like K218b straddle the border between gas giant and habitable world. With water vapor in its hydrogen-rich skies, it may host oceans beneath pink clouds. But gravity 3 times Earth's and crushing pressures below hint at life that is gelatinous, pressure-hardened, and unlike anything we know. Even binary stars can cradle Earth-like worlds. Kepler 1649c, 300 light-years away, orbits 2 red dwarfs. It may experience double sunrises that fuel hyper-efficient photosynthesis. Tidal forces from its twin suns could stir the core, adding geothermal warmth from within, a planet basking in heat from both above and below. In ultra-cool star systems like TRAPPIST-1, a year lasts only 20 Earth days. But the star's infrared glow can still power photosynthesis, albeit at just 1% of Earth's light. Plants here might evolve pitch-black leaves to drink in every photon, painting forests in obsidian hues. Moons could outshine their planets. Kepler 1625bi, a possible Neptune-sized exomoon, orbits a gas giant nestled in a habitable zone. Shielded by its planet's magnetic field, it might enjoy stable climates, even in flare-prone systems. A celestial sanctuary hidden in plain sight. Carbon-rich worlds like 55 Cancri could be treasure troves of diamonds. With surface temperatures over 2,000 degrees Celsius, it's a searing wasteland now. But as its star cools, carbon might crystallize into solid continents, forming glittering landscapes where silicon-based life evolves in forests of diamond. Some worlds don't orbit stars at all. Cubsur 2149 to 0403, a rogue planet, drifts through space untethered. Yet radioactive decay might heat underground oceans. There, chemosynthetic microbes could thrive, clinging to hydrothermal vents in pitch-black alien seas. Massive hyper-Earths like HD 40307G weigh 8 times more than Earth. Their magnetic fields are stronger, shielding life from cosmic radiation. Thick atmospheres may retain heat for eons, but gravity this intense could confine life to low plains or oceans where buoyancy counters the crushing force. Tidal worlds like GJ667cc are stretched and squeezed by nearby stars. This constant flexing sparks planetary quakes, churning nutrients across the globe. Life here could flourish in deep ocean trenches, riding shockwaves of heat and chemistry. But days last just hours, a planet caught in a cosmic spin cycle. Aquatic planets like TOI 1452b may be composed of up to 80% water. No continents, just endless ocean. Evolution might favor intelligent aquatic life, like cetaceans or jelly-like superorganisms. Tsunamis here would roam unchallenged, forming wave patterns larger than any earthly storm. Time itself is older on planets like PSRB 1620-26b, which formed over 12.7 billion years ago, 8 billion years before Earth. If life ever began there, it's had longer than any known ecosystem to evolve, transcend, or fade into fossilized legends beneath ancient strata. Some planets showcase pure survival. GJ 1132b lost its atmosphere to solar flares twice, and twice it regenerated one through relentless volcanism. It's a planetary phoenix, proving that even the harshest cosmic trials can be overcome. At the other extreme, KL-9b, a superheated gas giant at 4,300 degrees Celsius, orbits so close to its star that its atmosphere evaporates into space. Yet in that chaos, organic molecules escape, potentially seeding nearby planets with life's building blocks. Death here could spark life elsewhere. Eyeball planets like Gliese 581g are frozen on the dark side, but warm and wet on the side facing their star. At the center, a permanent liquid eye might support life in an icy desert. A strange oasis where day never ends and night never lifts. Planets with triple suns, like those in the HD 188753 system, endure wildly shifting years. Life here may evolve rapid adaptability, syncing its biology with chaotic light cycles. Imagine animals that hibernate, bloom, or breed with each new sunrise. Super-Earths with low-density cores could support floating continents, massive rafts of rock drifting on magma oceans. Kuro 7b, now a blazing inferno, might someday cool into such a world, its crust reshaping itself like a living planet's skin. Some planets have oxygen-rich atmospheres without any known life. GJ486b stunned scientists with water vapor and CO2, but it's likely volcanism, not biology, producing them. The next frontier is finding biosignature gases like phosphine or methane, clues of invisible ecosystems. Puffy planets like HAT P1b are so light they float like corks. Their extended atmospheres could support floating microcolonies, drifting through layered air currents. These skies might be alive, stacked like ocean layers with high-altitude ecosystems. Lava worlds, such as K2-141b, rain molten rock and possess supersonic winds. But over time, as stars age and dim, these infernos could cool into crusty, mineral-rich surfaces, perfect for future civilizations to mine, colonize, and adapt. Planets with titanic ring systems, like those speculated around J1407b, cast shadows that alter surface temperatures. Eclipses could last for decades, creating rhythmic seasons. Life might sync its reproductive cycles to these long, cosmic dimmings. Decades of growth, followed by decades of rest. In globular clusters, stars are tightly packed, neighbors just 1/1000th of a light-year apart. On planets in these regions, intelligent life might develop interplanetary cultures early, with other habitable worlds visible in the sky like neighboring cities. Steppenwolf planets, worlds ejected from their stars, may pass near black holes, where tidal heating ignites their cores. For brief cosmic moments, they become warm enough for life, wandering oases in the galactic night. Earth, often seen as the gold standard, is fragile. Our ice ages, asteroid impacts, and tectonic chaos contrast with the serenity of tidally locked worlds or stable orange dwarf systems. In the grand scheme, perfection is relative, and Earth is but one flavor in a cosmic buffet. The James Webb Space Telescope has opened a new era, decoding exoplanet atmospheres. Spectra now reveal oxygen, methane, even traces of industrial chemicals. Could we someday detect CFCs, not natural but signs of alien industry? Future missions like LUVOIR and HABEX will go further, imaging entire planetary surfaces. One glimpse of glowing cities or algal blooms would shatter our solitude, proving we are not the universe's only architects. While interstellar travel remains a dream, we may one day send life ahead of us. Imagine DNA vaults or AI-guided probes launching tardigrade-like organisms to alien worlds, seeding tailored ecosystems across the galaxy, terraforming by code. But discovery brings a dilemma. If we find a world teeming with microbial life, do we protect it or colonize? Do we become galactic gardeners or conquerors? These choices may define the legacy of humankind. As Earth confronts climate change and resource strain, exoplanets offer more than escape. They offer a challenge to expand not just our reach, but our understanding, to evolve into something greater, not just survivors, but stewards of life beyond Earth. Each exoplanet tells a story. And as we listen, we begin to see the galaxy is not empty. It is full of mirrors, worlds that reflect who we are and who we might yet become.